Bonding connects equipment or systems together to maintain equal potential. Grounding connects equipment or systems to the earth to prevent hazardous voltage buildup and provide a path for fault currents. You bond when connecting different metal objects or systems that are intended to be at the same voltage. You also bond when connecting the metal enclosures of electrical equipment to avoid shock hazards. You further bond when connecting the metal frames of buildings, equipment, and structural components to equalize potential and prevent arcing. You ground when connecting the exposed conductive part of electrical equipment to earth ground. You also ground when connecting the neutral conductor of a supply system to earth ground. You further ground when connecting the grounding electrode conductor to earth ground. NEC Section 250.66 requires bonding of piping, enclosures, equipment frames, and other conductive materials to equalize potential and prevent shock hazards. NEC Section 250.122 provides guidelines for grounding electrical systems, including the grounding of service equipment, equipment enclosures, and the neutral conductor. Bonding is about creating equal potential and preventing shock hazards. Grounding is about protecting against fault currents and preventing hazardous voltage buildup. Bonding is typically done with metal connectors, while grounding requires a connection to the earth ground using a grounding electrode. The purpose of bonding is to establish an electrically conductive path between different metal parts or equipment. This path ensures that all connected parts are at the same electrical potential, minimizing the risk of electric shock. Bonding is crucial in preventing voltage differences that can occur due to various factors such as induction, static electricity, or stray currents. One common application of bonding is in electrical panels and enclosures. By bonding the metal enclosures of electrical equipment, any fault current that might occur will have a low impedance path back to the source. This low impedance path helps to quickly trip the circuit breaker or fuse, disconnecting the power and preventing a dangerous shock. Another critical area for bonding is in metal piping systems, such as water pipes or gas pipes. These pipes can become energized due to contact with electrical wiring or equipment. Bonding these pipes together into the electrical grounding system helps to ensure that they remain at a safe potential. Bonding is also important in structural steel buildings. The steel frames of buildings can act as conductors, and differences in potential can develop between different parts of the structure. Bonding the steel members together helps to equalize the potential and prevent arcing or sparking, which can be a fire hazard. When it comes to specific bonding applications, there are several key considerations. Firstly, the bonding connections must be mechanically sound and electrically conductive. This means using appropriate connectors and ensuring that the connections are clean and tight. Secondly, the bonding conductors must be sized correctly. The size of the bonding conductor depends on the size of the circuit conductors or equipment it is serving. NEC Section 250.102 provides guidance on sizing bonding conductors. Thirdly, the bonding path must be continuous. There should be no breaks or discontinuities in the bonding path, as this can compromise its effectiveness. Grounding, on the other hand, is about connecting electrical systems and equipment to the earth. The earth acts as a reference point for electrical potential, and grounding helps to stabilize the voltage of electrical systems. Grounding also provides a path for fault currents to flow back to the source, which helps to quickly trip the circuit breaker or fuse and prevent electrical shock. There are two main types of grounding: system grounding and equipment grounding. System grounding refers to the grounding of the neutral conductor of a supply system. This is typically done at the service entrance, where the neutral conductor is connected to a grounding electrode, such as a ground rod or a metal water pipe. System grounding helps to stabilize the voltage of the electrical system and provides a path for ground fault currents. Equipment grounding refers to the grounding of the non-current carrying metal parts of electrical equipment, such as enclosures, frames, and motor housings. This is done to provide a low impedance path for fault currents to flow back to the source, which helps to quickly trip the circuit breaker or fuse and prevent electrical shock. When it comes to specific grounding applications, there are several key considerations. Firstly, the grounding electrode must be effective. This means that it must be in good contact with the earth and have a low resistance to ground. NEC Section 250.52 provides guidance on grounding electrodes and their installation. Secondly, the grounding electrode conductor must be sized correctly. The size of the grounding electrode conductor depends on the size of the service entrance conductors. NEC Section 250.66 provides guidance on sizing grounding electrode conductors. Thirdly, the grounding path must be continuous. There should be no breaks or discontinuities in the grounding path, as this can compromise its effectiveness. The relationship between bonding and grounding is critical for electrical safety. Bonding and grounding work together to provide a safe and reliable electrical system. Bonding ensures that all metal parts and equipment are at the same electrical potential, while grounding provides a path for fault currents to flow back to the source. By combining bonding and grounding, the risk of electrical shock is minimized. Understanding the difference between bonding and grounding is essential for anyone working with electrical systems. Bonding is about creating equal potential, while grounding is about providing a path for fault currents. Both bonding and grounding are necessary for electrical safety. In addition to the basic principles, there are specific code requirements that govern bonding and grounding. The NEC provides detailed guidelines on how to properly bond and ground electrical systems and equipment. It is important to be familiar with these code requirements to ensure that electrical installations are safe and compliant. For example, NEC Section 250.4 provides general requirements for grounding and bonding. This section outlines the basic principles of grounding and bonding and provides requirements for the installation of grounding and bonding conductors. NEC Section 250.24 provides requirements for grounding the neutral conductor of a supply system. This section specifies the methods for grounding the neutral conductor and provides requirements for the size of the grounding electrode conductor. NEC Section 250.92 provides requirements for bonding metal enclosures and other non-current carrying metal parts. This section specifies the methods for bonding these parts and provides requirements for the size of the bonding conductors. To summarize, bonding and grounding are two distinct but interconnected concepts in electrical safety. Bonding focuses on creating an electrically conductive path to equalize potential between different metal parts, thereby minimizing shock hazards. Grounding, on the other hand, connects electrical systems to the earth, providing a reference point for voltage and a path for fault currents to safely return to the source, triggering overcurrent protection devices like circuit breakers. Remember that bonding uses metal connectors to link equipment, while grounding connects to an earth-ground electrode. NEC sections like 250.66 and 250.122 offer detailed guidance on implementing these principles in various electrical installations, and understanding these code requirements is crucial for ensuring electrical safety and compliance. Let's delve a little deeper into specific scenarios where bonding and grounding are applied, highlighting the practical differences and code requirements. Consider a typical residential electrical panel. The metal enclosure of the panel must be bonded to the grounding system. This is typically achieved by connecting a bonding jumper from the neutral busbar to the panel enclosure. This ensures that the panel enclosure is at the same potential as the neutral conductor, minimizing the risk of electric shock if someone were to touch the enclosure while a fault exists. In addition to bonding the panel enclosure, all metallic conduits entering the panel must also be bonded. This is typically done by using bonding bushings or clamps that connect the conduit to the panel enclosure. This ensures that any fault current that might flow through the conduit will have a low impedance path back to the source, tripping the circuit breaker. Now let's consider a commercial building with a large motor. The motor enclosure must be grounded to provide a path for fault currents. This is typically done by connecting a grounding conductor from the motor enclosure to the equipment grounding conductor in the circuit. The equipment grounding conductor is then connected back to the grounding electrode at the service entrance. This ensures that any fault current that might flow through the motor enclosure will have a lower impedance path back to the source, tripping the circuit breaker. In addition to grounding the motor enclosure, the motor frame must also be bonded to the building steel. This is typically done by connecting a bonding conductor from the motor frame to the building steel. This helps to equalize the potential between the motor frame and the building steel, preventing arcing or sparking. Another important application of bonding and grounding is in swimming pools. Swimming pools are particularly susceptible to electrical hazards due to the presence of water and the close proximity of electrical equipment. All metal parts within a certain distance of the pool must be bonded together to create an equipotential bonding grid. This includes the pool reinforcing steel, metal piping, and metal equipment. The equipotential bonding grid helps to equalize the potential in the pool area, minimizing the risk of electric shock. In addition to bonding, swimming pools must also be grounded. The pool equipment, such as the pump and filter, must be grounded to provide a path for fault currents. The grounding conductor is typically connected to the equipment grounding conductor in the circuit. Now let's talk about sizing the bonding and grounding conductors. The size of the bonding and grounding conductors depends on the size of the circuit conductors or equipment they are serving. The NEC provides tables that specify the minimum size of the bonding and grounding conductors based on the size of the circuit conductors. For example, NEC section 250.102 provides guidance on sizing bonding conductors for equipment grounding. This section specifies that the bonding conductor must be sized no smaller than the equipment grounding conductor for the circuit. NEC section 250.66 provides guidance on sizing grounding electrode conductors. This section specifies that the grounding electrode conductor must be sized based on the size of the service entrance conductors. It is important to note that the NEC is a minimum standard. In some cases, it may be necessary to use larger bonding and grounding conductors to ensure adequate safety. For example, in areas with high levels of electrical noise or interference, it may be necessary to use larger bonding conductors to reduce the risk of electrical problems. It's also worth noting that bonding and grounding requirements can vary depending on the type of electrical system and the specific application. For example, the requirements for bonding and grounding in a healthcare facility are different than the requirements for bonding and grounding in a residential dwelling. Healthcare facilities have more stringent requirements due to the presence of sensitive medical equipment and the increased risk of electrical shock. To further illustrate the practical applications, consider a scenario involving sensitive electronic equipment such as computers or servers. These devices are particularly susceptible to damage from electrical noise and transients. Proper bonding and grounding are essential for protecting these devices. The equipment enclosures must be bonded to the grounding system to provide a low impedance path for noise and transients. This helps to prevent these disturbances from interfering with the operation of the equipment. In addition, surge protective devices should be installed to protect against voltage spikes. These devices divert excess voltage to ground, preventing damage to the equipment. In industrial settings, bonding and grounding are critical for preventing explosions and fires. Many industrial processes involve flammable materials, and electrical sparks can ignite these materials. Proper bonding and grounding can help to prevent the buildup of static electricity and reduce the risk of sparks. All metal equipment and piping must be bonded together to create an equipotential bonding grid. This helps to equalize the potential in the area, minimizing the risk of sparks. In addition, grounding electrodes should be installed to provide a path for fault currents. These electrodes help to quickly trip the circuit breaker or fuse and prevent a dangerous buildup of voltage. The inspection and testing of bonding and grounding systems are also essential for ensuring electrical safety. Regular inspections can help to identify any problems with the bonding and grounding system, such as loose connections or corroded conductors. Testing can be used to verify that the bonding and grounding system is performing as intended. There are several different types of tests that can be performed, such as ground resistance testing and continuity testing. Ground resistance testing measures the resistance of the grounding electrode to earth. This test is used to verify that the grounding electrode is effective. Continuity testing verifies that the bonding and grounding conductors are continuous and have low resistance. This test is used to identify any breaks or discontinuities in the bonding and grounding path. In conclusion, bonding and grounding are essential for electrical safety. Bonding ensures that all metal parts and equipment are at the same electrical potential, while grounding provides a path for fault currents. By combining bonding and grounding, the risk of electrical shock is minimized. It is important to understand the difference between bonding and grounding and to follow the NEC requirements for bonding and grounding electrical systems and equipment. Regular inspection and testing of bonding and grounding systems are also essential for ensuring electrical safety. Remember that understanding the theoretical underpinnings of bonding and grounding is just as important as knowing the practical applications and code requirements. Bonding and grounding are not merely about following rules, they are about understanding the physics of electricity and how to create a safe electrical environment. By understanding the underlying principles, you can make informed decisions about how to design, install, and maintain electrical systems. Firstly, always consult with a qualified electrical professional for any electrical work. Electrical work can be dangerous, and it is important to have the expertise of a qualified professional to ensure that the work is done safely and correctly. Secondly, always follow the NEC requirements for bonding and grounding. The NEC is a comprehensive set of standards that provides detailed guidance on how to properly bond and ground electrical systems and equipment. Thirdly, always use high-quality materials and equipment. The quality of the materials and equipment used in bonding and grounding systems can have a significant impact on their effectiveness. Fourthly, always inspect and test bonding and grounding systems regularly. Regular inspection and testing can help to identify any problems with the bonding and grounding system and ensure that it is performing as intended. By following these guidelines, you can help to create a safe and reliable electrical system.